In this video we're going to see how we can solve second order differential equations. This is the general form for a second order differential equation. We've got a d2y by dx squared plus b dy by dx plus cy equals 0, where a, b and c are constant values. Hopefully you can see why it is a second order differential equation. That's because the highest derivative here is the second derivative. So this is different to previous differential equations where we've only focused on a dy by dx, a first order. This is just what we call a homogeneous second order differential equation because it equals 0. We're going to see in a later lesson how we can solve non-homogeneous second order differential equations where this isn't 0. So I want to find a solution to this equation. I want to find what y could equal. Now, I'm going to show you what it can't equal first, and then hopefully you can see what it will, why we're going to end up with the solution that we do end up with. I'm going to take a guess at this. I'm going to say, well, what about if we thought that the solution could be a quadratic equation? If I just took a wild guess and thought, well, maybe this is the solution to a second order differential equation. And now I'm going to show you why a quadratic can't be the solution to this. And then hopefully it'll make sense why I do the next step in a minute. So, if I thought that this was my solution for y, then the first derivative of this would be this, and the second derivative of this would be that. Substituting these into this equation would give me a times 2 plus b times 2x plus 3 plus c times x squared plus 3x plus 5 equals 0. So this is me just substituting these into that equation. Now, there is no combination of a, b and c here that this could work for all values of x. Notice we've got an x squared here, and there is no other x squared term here. So there's no x squared term here that will cancel this out to make 0. There's no way possible that this can be a solution for this for all values of x. So the quadratic won't work here because the x squared won't cancel out with anything else. So what I actually need is a function where when I differentiate it and then differentiate it again, I get something that will cancel out. So that is why my guess is going to be an exponential function. Because I know that when I differentiate an exponential function, I get the exponential function. And then when I differentiate it again, I will still get the exponential function. Then I will get some cancellation where this can actually equal 0. So that's why I've done the e to the power x here. And the a and the m are just constants because I want to find a general solution for this. I don't want to talk about specific solutions. I want to be as general as possible. So there might be a coefficient of the x up here, and there might be a coefficient at the front here. So this is just a really general exponential function. And let's see what would happen if I tried to substitute that into here. So let's work out the derivatives of this. So if I differentiate this, we know the exponential, when I differentiate it, stays as the exponential. And then by the chain rule, I have to multiply by the derivative of the inside here, so times by m. Now I differentiate again. So when I differentiate this again, this is going to stay the same, and I have to multiply by the derivative of the inside, so multiply by m again. If I now substitute each of these into that original equation, I get a times all of this, plus b times all of this, plus c times all of this equals 0. What I can do now I notice that I've got an ae to the mx in both of in all three terms here. So I'm going to factorise that ae to the mx outside. Now I know that this ae to the mx here, because it's an exponential function, I know it can't equal 0. The exponential function never equals 0. Hopefully we remember that from our work in regular maths. And obviously if I was saying that a equaled 0, then that original function would be 0. And then I'm saying that 0 plus 0 plus 0 equals 0. So that would be a trivial solution. So that's why we can say with confidence that this whole thing here is not going to equal 0 to find our solution. Therefore, what I can say is this bit here must equal 0. This is what we call the auxiliary equation, and it's really important for second order differential equations. So let's have a look about what this tells us about our solutions, and there are several different cases that we need to consider. So case number 1. So we've got our original general differential equation here, and we've got the auxiliary equation that comes from that. First case I want to consider is when this auxiliary equation has two distinct roots. And we know that's going to be the case when the discriminant of this is positive. So, if there are two distinct roots of this equation, I'll call them alpha and beta, then the general equation would be y equals ae to the alpha x plus be to the beta x. So the sum of our two guesses from before, where obviously alpha and beta are our two different roots of this auxiliary equation. So let's have a look at an example and we can see why this works. So here is a specific second order differential equation. First thing I'm going to do is write down the auxiliary equation for this. So a is 2, b is 5, c is 3. So our auxiliary equation is 2m squared plus 5m plus 3 equals 0. When I solve that equation, I find that either m is minus 3 over 2 or m is minus 1. So these are the two roots. So that allows me to write down our general solution as being y equals ae to the minus 3 over 2x plus be to the minus x. This is my solution to this equation. And just to prove that that works, let me show that when I substitute this in here, I do get 0. So when I differentiate it, I get that. When I differentiate it again, I get that. Then when I substitute these in, so I've got, when I substitute each of these into the original equation, so I've got 2 lots of the second derivative. So when I times all this by 2, I get this. Then I've got 5 lots of the first derivative, so 5 lots of all of this gives this. And then I've got 3 lots of the y, which gives this. And hopefully you can see here, if we let's focus on the b parts. 2b to the minus x minus 5b to the minus x plus 3b to the minus x. Hopefully you can see there, they cancel out. And similarly, if we were to add these 3 terms here together, so those 3 terms here, they would cancel out. This, and this cancel out. Therefore, this does equal 0 for all values of x. And this is a solution to this second order differential equation for all values of x. So, if our auxiliary equation has 2 distinct roots, alpha and beta, then our general solution will just look like that, where basically our 2 solutions to the auxiliary equation will be the coefficients of the power here and here. The values of A and B will be worked out at a later stage, basically, a later lesson. We would find those once we know some boundary conditions. So once we know some values of x and y that we can actually substitute in here to help us to work out the A and the B. Right, so that was if we had two distinct roots. What about if there was actually a repeated root to this? We know that there's a repeated root to the auxiliary equation when the discriminant is 0. So what would happen then is if there was a repeated root, and that root is just alpha, then our general solution would look like this. It would be a plus bx, where a and b are just constants to be worked out later, multiplied by e to the alpha times x, where alpha is the solution, the one repeated solution to this equation. Let's look at an example. So here is my differential equation. So the auxiliary equation looks like that. The one repeated solution to the auxiliary equation is m equals 3. So alpha is 3 now. So there is my general solution to this. And again, just to prove that this is a solution to this, I'm going to differentiate this once, then differentiate it again, and then substitute them in and show that it does cancel out and give 0. In order to help me differentiate this, I've just expanded the brackets, and then when I differentiate it once, differentiating this gives this, differentiating this with the product rule gives this. Then differentiate again, we get all of that. So differentiating this gives this, differentiating this gives this, differentiating this with the product rule gives this and this. Then substituting all of this into the original equation here. So when I substitute this in up here, I've got that there. This and this add up to make this, plus this. Then minus 6 lots of all of this, plus 9 lots of the original. So that gives that. And then if you want to follow all of that through there, then you can see that actually then if I collect up the like terms here, we can see they all cancel out. If I collect up the like terms here, here, and here, they all cancel out. And basically all of this cancels out for all values of x and does give me 0. Which means that this is a solution to this equation for all values of x. And again, we can work out the a and the b with some boundary conditions in a little while. Right, the next case we've done if there is two distinct roots, we've done if there is a repeated root. What about if there are no real roots to this auxiliary equation? There's two different cases we need to look at in this case. So we know that no real roots happens when the discriminant of this equation is negative. Now, let's look at an example. Before I just tell you what the general equation is in this specific case, let's work it through an example. So here is my second order differential equation. We can see in this case that my a is 1. The b in this case is 0 because I've got no dy by dx. And the c is 16. So my auxiliary equation looks like that. When I solve that equation, when I take the 16 to the other side and square root, I find that m is either plus or minus 4i. So we have an imaginary solution here. If I start off with my general solution like we did when we had our two distinct roots from before, so if I were to assume it was like this to begin with alpha being 4i and beta being minus 4i, I could write my general solution like that. However, we know from our work on complex numbers that e to the 4ix can be written as cos 4x plus I sine 4x. So with that in mind, I could rewrite this a times e to the 4ix as being a times all of this. And similarly, I could rewrite the e to the minus 4ix as all of this. And then if I were to expand out those brackets, and then to collect up like terms, so I've just expanded this bracket here and expanded this bracket here, then I've collected the a cos 4x plus b cos 4x over here, and then I've expanded, I've got the a times I sine 4x, and then I've got the b times minus I sine 4x. I factorised out the cos 4x here and here, which leaves me with just an a plus b. And then over here I factorised out the sine 4x to leave an I, a minus b at the front. And the reason why I've done all of this is actually a plus b, remember a and b are constants. So this is just a constant at the front, and I can replace a plus b with a different constant. I've called it p here, but it's just another number to be worked out with our boundary conditions later. Similarly, the I times a minus b is just a constant number. We don't need to worry about that being any more complicated, and it's just a number to be worked out with our boundary conditions later. So, rather than writing it in this complicated form, we could just write it like this. So, if an auxiliary equation has two imaginary roots, we'll call the first one I omega and the second one minus I omega, then the general solution will look like that, where it's y equals a cos omega t plus b sine omega t. Right, one final case to consider. The auxiliary equation with no real roots, part 2. So starting off exactly the same as the previous one, but we'll see in this example what's different. So that's our second order differential equation. So we'll write down our auxiliary equation to begin with. And we will solve that auxiliary equation. And we can see now that we have two complex solutions to this auxiliary equation. Previously, in that last example, our two solutions to the auxiliary equation were imaginary. There was no real part involved here. Now we do have a real part involved. So our solutions are complex. But we're going to follow through the next few stages just like before. If I continue with the general equation from here that we started off with, alpha and omega being my 3 plus 5i and 3 minus I. That's a form of the general solution, but it's a very complicated form, so we're going to rewrite this. First thing I'm going to do is just expand out those brackets at the top there, so 3 times x, 5i times x, 3 times x minus 5i times x. I am now going to use the laws of indices to allow me to rewrite this. If my powers are being added here, then that's just like me multiplying these two things together. And again, over here, if I've got 3x plus minus 5ix, then that's just like me multiplying with the minus here. So I'm just splitting these powers up using the laws of indices. And that's helpful because I've got an e to the 3x here and e to the 3x here, which I can factorise out. And this bit on the inside here is pretty much what we did in the last case. So we know that we can rewrite this. You know, in the last example where we had, where we saw that we could rewrite the 4ix, so the a e to the 4ix plus b e to the minus 4ix, we saw that we could rewrite that like this. The only difference here is it's not a 4, it's a 5. Yeah, it's not a 4, it's a 5. Therefore, it will be a 5 here and here instead. So basically, the step from here to here is exactly the same as what I've just done here. So, this is the final case. If our auxiliary equation has two complex roots, p plus or minus iq, then the general solution to that differential equation will be y equals e to the p x. So here it was e to the 3x, so it'd be e to the px generally, multiplied by a cos q x plus b sine qx. And again, you would be able to get some boundary conditions to actually be able to work out what the a and the b are. The p and the q here and here have obviously come from the roots of our auxiliary equation. So quite a lot of stuff I've covered there. This is a summary to get copied down. So copy that summary down. And there we go.